Hi everyone, welcome to my talk. My name is Wenjiao Chen, and today I would like to share with you some of my drawing work with Keegan Boyle. Both of us are currently postdocs at the University of British Columbia, and we would like to thank the organizers for the opportunity to share our work. And today my title is Coordinated Amphichiral Knots and the half-Conway polynomial, and I hope by the end of the talk, I'll be able to tell you what these things are and convince you that half-Conway polynomial is really useful invariant for studying amphichiral knots. And let me just begin by recalling some of the basic definitions. So here, we're going to be looking at strongly negative amphichiral knot, and I'm going to call it a snag for short. So a snag is a knot K along with an order 2 symmetry rho, which simultaneously reverses the orientation of S3 and K. And it has a fixed set consisting of 2 points. So let me just remark that in our definition, we're thinking of the symmetry rho as part of the definition. So a snag is a pair K and rho. And this is slightly different than what you can find in the literature, in which sometimes we just think about a knot as a snag if it admits such symmetry. Okay. And again, here's the first example of snag. This is the figure 8 knot, and I'm sure most of you would agree with me that this is a snag. And you might also have done the exercise of finding an isotopy from this knot to its mirror image. But the first thing I learned from Keegan is that suppose you want to think about the amphichiral symmetry on the figure 8 knot, then this is really the wrong diagram you should look at. And you're supposed to look at a diagram in this form. And here you should think about the left end and the right end of the knot of the diagram drawing at the infinity. So you have a knot in S3, and also the symmetry is just the point reflection about the center point here, which is highlighted by a fat dot. And once you do the point reflection, you can see the knot the center itself. And there are 2 fixed points. One is the center, and one is infinity. So this figure knot is a snag. And such a diagram is called a symmetric diagram. And it's a fact that every snag admits a symmetric diagram. And in addition to allowing you to visualize the symmetry on the knot, symmetric diagram also allows you to cook up some diagrammatic invariants of snag. And for example, here's one of such invariant you can find in our paper. It's called half-linking number. Let me just tell you what it says. And let's just first look at symmetric diagrams in slightly more detail. And this is a symmetric diagram for the figure 8 knot again. And I have added a pair of symmetric Reidemeister-1 moves here. And you'll see why in a minute. The first thing to notice is that the 2 fixed points on the knot actually separates the knot into 2 arcs. I've drawn them in red and black so that you can see it. And the second thing is that all the crossings in this diagram come in pairs. For example, if you have a crossing here, then applying the symmetry about this point, you reflect about this point, it's going to tell you there's a crossing down here. Okay. And the fact that you have 2 arcs, the red arc and the black arc, actually allows you to distinguish symmetric pair of crossings into 2 types. For example, like this crossing on the far left and the crossing on the far right, they form a pair of crossings called monochromatic crossings. And basically that means the crossings within that pair just appears within 1 arc. Like this crossing is all between black arc and this crossing is all between the red arc. And while these 2 crossings in the middle, they form something called dichromatic crossings. And you can see the crossings occur between the red arc and the black arc. And the third thing to notice is that if you look at a symmetric pair of crossings, then the signs of the 2 crossings are always opposite to each other. One is like this guy is negative and this guy is positive. However, there's a way to assign a sign to every pair of crossings using the orientation of the knot. And here's the way to do it. So let's just look at these two closings, for example. And what I'm going to do is I'm going to start from one of the fixed points, say at infinity. I'm going to traverse the knot along the orientations. I'm going to traverse the knot like this. And I'm going to see this closing first. And then I'm going to continue. I'm going to see this is the second closing that appear in the symmetric pair. And what I'm going to do is I'm going to demand that. I'm going to declare that the sign of the second closing I see is the closing of the pair of the diclot of this pair. So in here, this sign is positive just because the sign of this closing is positive. And you can do that for these two pairs, for these two closings as well. And once you know that, then you can define the half linking number to be 1/2 times the sum of the signs of all the dichromatic closings. So notice that we do not include monochromatic closings in the definition. That's basically because you can actually add many randomized-to-1 moves as you want in whatever signs you want. So for sure, you won't get an invariant that way. And let me just to finish, let's look at an example to make sure we understand the definition. So in this figuring out diagram, so there are two pairs of dichromatic closings, in gray and one in red, and both of them, the signs are given by the signs. You can figure out the signs are positive. So you can see the half linking number is 1/2 times 1 plus 1 is 1. That's what it is. And basically, you can check that the half linking number is an invariant of the snack by checking that, by verifying that it is invariant under a set of equivariance randomized moves. So any two symmetric diagrams of a snack is connected by finite to many equivariance randomized moves. And you have seen an equivariance randomized to 1 move. And I'm sure you can imagine what randomized to 2 and 3 moves will look like in this context. And the only difference in our case is that there's also an extra move called equivariant R4 move, which is basically an R2 move, but it crosses the fixed point in the middle. Okay. And once you know that, checking this is invariant is elementary, so I'm going to skip that. And basically, now you can see the half linking number is like the linking number between the two arcs. And it's a quite funny invariant if you think about it, because you're only counting the sign of half of the closings, and that's why there's a half in its name. When we first learned the definition of the half linking number, we were a little bit, unsatisfied in the sense that, hey, the usual linking number has a homological interpretation, and what about a half linking number? So really what it says, why just summing like half the closings we give an invariant? And indeed, considering this question has led us to a much more refined invariant, which is called which is the half-Conway polynomial that I would like to tell you. And there are two approaches to think about the half-Conway polynomial. One is homological, and the other one is diagrammatic. And I'm going to begin with the homological approach. And indeed, I'm going to tell you what the half-Alexander polynomial is first. And then I'm going to tell you how to get the half-Conway polynomial from the half-Alexander polynomial. So in fact, the half-Alexander polynomial already made its appearance in 1979. So Hartley and Kouachi proved if you have a snack, K and rho, and the Alexander polynomial of that snack, that's denoted by delta K of t, then if you replace t by tau square, then this polynomial actually factors as f of tau times f of tau to the inverse for some integer coefficient Roland polynomial f of tau. Here we're using a dot equal because all these things are defined up to multiplication of a unit in this Laurent polynomial ring. And so basically this f of tau here, this vector is the half Alexander polynomial for the knot k and rho. And it was actually first studied by Kawauchi in a slightly broader context. And here, let me just tell you the definition for a snack. So for snack, to get the half Alexander polynomial, the first thing we do is we look at the knot complement of the snack and record that there's an order 2 symmetry rho, and that order 2 symmetry actually restricts to an order 2 symmetry on the knot complement. And it's fixed point free because the fixed point are on the knot, and now you remove the knot. And so you can take a portion of the knot complement, and you're going to get n manifold. You're going to denote that by Q. And what Kawauchi showed us that this Q is actually a non-orientable integer homology S1. And once you have an integer homology S1, then you can define the Alexander polynomial of this manifold using the standard machinery. So basically, you can just look at the infinite cyclic cover of Q, and the first homology of that infinite cyclic cover is now a Z adjoint tau to the -1 module, where the tau action is induced by the deck transformation. And the principal generator of the first elementary ideal here is the Alexander polynomial. And basically, that was the homological approach. And the half-Conway polynomial as a suitable normalization of the half-Alexander polynomial. So it's basically just an integer coefficient polynomial in Z variable, and it has constant term equal to 1. And if you're plugging tau minus tau to -1, you're going to get back to the half Alexander polynomial of the snack. And this is just really similar to the usual way people normalize the Alexander polynomial. Just to make sure that get this definition. So for example, for the figuring out, we have the half Alexander polynomial is equal to 1 plus tau minus tau to the -1. And the half Conway polynomial is just 1 plus Z. Okay. And the reason that we normalize this half Alexander polynomial in this way is because it allows us to phrase a different perspective on the half Alexander polynomial. And indeed, the half-Conway polynomial satisfies an equivariant version of the scaling relation. So let me tell you what it says. So suppose you have 3 knots, k plus, k minus, and k0, such that k plus and k minus differ at a pair of dichromatic crossings, and where the dichromatic crossing pair in k plus is positive and in k minus is negative, and k0 is not obtained by doing resolutions at the pair of crossings, then these 3 knots, their half-Conway polynomial satisfy this relation in the middle here. So the half-Conway of k plus minus half-Conway of k minus is equal to Z times the half-Conway of k0. And so this guy actually is what I call the diagrammatic approach of the half-Conway polynomial, because essentially just like you can compute the Conway polynomial using scaling relation, you can do it the same way here for the half-Conway polynomial. You can just keep applying this equivariant scaling relation to reduce the computation of half-Conway to knots without dichromatic crossings. In those cases, half-Conway polynomial is very simple. And so now I think it's not a surprise to say that, tell you that the z coefficient of the half-Conway polynomial is equal to the half-linking number. Basically, you can see from the scaling relation that the z coefficient just remembers the closing change information of diagrammatic closings. Okay, and this is the diagrammatic approach to the half-Conway polynomial. And in addition to refining the half-linking number, there are also a bunch of fun applications that I would like to tell you in the remaining time. So the first set of applications that it actually answers two questions in the literature. The first question is due to Houghton and Kouachi, and what they ask is which polynomials are realized as the half-Alexander or half-Conway polynomial of a snack in S3. So what we found out is that actually for any polynomial with constant term equal to 1, you can find a snack such that its half-Conway polynomial is equal to that given polynomial. And indeed, our proof is constructive. So we just explicitly construct such a knot for any given polynomial. And the second question, seemingly unrelated in the beginning, is due to Menelauscu. So what he asked is whether there are any non-slice amphichiral knots of determinant 1. Here, a knot is non-slice if it doesn't bound any disks in the forebore. And a knot is said to have determinant 1 if and only if its twofold branch cover is an integer homologous sphere. And actually, one of the motivation for this question is if such knot exists, then the twofold branch cover of these knots would provide potential non-trivial torsion elements in the homologic quadratism group of integer homologous spheres. And it's still an open question whether such a non-trivial torsion element exists. And but nevertheless, Keegan and I are able to answer the question on the knot level. So there indeed are non-slice snacks of determinant 1, and this is an example. And you can see the knot on the right is just the usual knot diagram. It's a pretty complicated knot, so it's not surprised like why such knots were not known before. But of course, this is far too complicated for us to come up with. So indeed, in the beginning, we were looking at diagrams of this form on the left. So this is called a symmetric surgery diagram for a snack. You can see there's an obvious symmetry on the surgery diagram. And one of the good things about working with such a surgery diagram is that you can look at the infinite cyclic cover of this diagram. And in there, you will have a surgery representation of the infinite cyclic cover. And so that you can actually use that surgery representation to compute the half-Alexander module or half-Alexander polynomial of the knot. And you can basically just changing the closing information of the length of the surgery length here to obtain any type of half-Conway polynomial you want. And basically, that's how we answer Houghton and Kouachi's question. And in this question, we just choose this surgery length here in such a way that we're going to have a very, very specific half-Alexander polynomial. So let me be slightly more concrete. So we just choose the surgery diagram in such a way that we're going to have a snack whose half-Alexander polynomial is equal to this weird thing here. You don't have to remember these. Like the reason we want this guy is because we can use the Hartley-Kouachi's theorem to compute its Alexander polynomial. And the Alexander polynomial would be something of this form. And again, please don't try and remember what these things are. The whole point is if a snack has such an Alexander polynomial, then you can compute its determinant. And you can find the determinant as 1. And also, you can apply the Fox-Muller condition to show the knot is not slice. And just recall that the Fox-Muller condition says if a knot k is sliced, then the Alexander polynomial will factor as g of t times g of t to -1 for some integer polynomial, integer coefficient polynomial. And basically, we just want these two properties. So this Alexander polynomial does not factor like this. So the underlying knot is not sliced. And finally, let me just remark that here, the Hartley-Kawasaki factorization and the Fox-Muller factorization are a little bit different. Okay, so this is a factorization of the Alexander polynomial evaluated at tau square, while this is just t. So they're not the same thing. And here's the second application, is also on knot concordance. So first record that as a really well-known theorem due to Friedman, which says if you have a knot and its Alexander polynomial is trivial, then you know the knot is topologically sliced. And when you're considering concordance of snacks, it's also natural to ask whether a snack is equivariantly sliced. And equivariantly sliced would mean the knot is sliced, meaning it bound to a sliced disk in four-ball, and also means the symmetry of the knot extend over the four-ball in such a way that it restricts to a reflection on the sliced disk. And what Keegan and I found out is that if you have a snack and the Alexander polynomial of that snack is trivial, then Friedman's theorem can actually be strengthened to say that the knot K is equivariantly topologically sliced. And as you notice here, I put the quotation mark on the application. The reason is that the proof of this theorem actually doesn't use the half-Alexander polynomial at all. It uses something called surgery theory. But this theorem does connect to the half-Alexander polynomial in some heuristic way. Indeed, back in '76, Kawasaki proved that if you have a snack and you know it's equivariantly sliced, then the half-Alexander polynomial actually factors as g of tau times g of negative tau to -1 for some integral polynomial g. So this is something very similar to the Fox-Muller condition. And it is learning such a theorem exists somehow suggests us to prove an equivalent version of Friedman's theorem. And also, if you know a little bit more about concordance of knots with symmetry, then you'll be slightly more surprised by the results because you can it's actually, I mean, like it's not necessarily true that you can generalize Friedman's theorem to knots with any other symmetries. For example, there are strongly invertible knots, and they have trivial Alexander polynomial, but they're not equivalently sliced. So somehow the existence of the half-Alexander polynomial is a key thing in the background that why one can hope to prove a version of Friedman's theorem in this context. Okay, and that brings me to almost the end of the talk. I would like to take the opportunity to share with you some open questions that might be interesting. So there are many of these. For example, can you find amphichiral knots with trivial Alexander polynomial that's not smoothly sliced? So this is something stronger than Menelauskas' question, and we still don't know the answer. And maybe an easier question would be, can you find a snack and it has trivial Alexander polynomial, but it's not equivalently smoothly sliced? Okay, so we prove it's always topologically sliced, but can you do it for smoothly? So we still don't know the answer to this question. And here's the last question. So we know that knot phenomenology categorifies the Alexander polynomial. So is it possible to do the same thing for the half-Alexander polynomial? So I think this question might be interesting because answering it might be able to, help with answering the second question. And also, it might let us one step closer to defining Higgs homology for unorientable three manifolds, if that exists. And let me just mention that there are a couple of other open questions we listed in our paper, but I couldn't manage it to fit it in the talk. So if you're interested, please take a look and feel free to solve any subset of the questions. And also, if you have any other questions regarding the talk, please feel free to post it on Discord or come to my office hours. And other than that, let me just stop here. And thank you so much for watching.